friction. 11 to 21. Odds. Let's do it. All right. A 68-kilogram crate is dragged across a floor by pulling on a rope attached to the crate, inclined 15 degrees above the horizontal. That sounds familiar. Seen that before. 68 kilograms. And the coefficient of static friction is 0.5. What's the minimum force to get it moving? All right. I think we need ourselves a force diagram. This is not on a ramp. Don't be fooled by that 15-degree angle. So all the forces here are going to be lined up with my regular old straight up and down axes. I don't know what this force is. That's what we're looking for. But I do know that this is F cosine 15 and this is F sine 15. And then I know this normal force. Well, I know that the normal force in this would have to balance that. So this would, I guess, have to be 68G, that's this, minus F sine 15. And if we're just on the verge of getting it moving, that is where this force would have to match the maximum amount of static friction. And that maximum amount of static friction is the static coefficient times the normal force, which I'm just going to write as Fn. I've got an expression for it there, but it would be that. All right, so let's see. I need to set some things equal to each other, figure out what to do here. So I know that, let's see, static friction, force of static friction, which would have to equal this. So F cosine, I don't know why I'm writing that as a subscript, that's weird, F cosine 15, this would have to be equal to this. And that is 0.5 times the normal force. And hopefully, you know, if everything's going our way here, there shouldn't be any more variables than just the one unknown force. And that looks good. It looks like that is true. So I think I need to do some math now. Let's see. What is the... Just checking to make sure I'm in degree mode there. The cosine of 15, that's going to be 0.966 F is equal to 68 G. Half of that is 333. I'm going to keep 3 sig figs on things. That should be okay. And then distributing that in here, half of a sine of 15, sine 15 over 2 is 0.129 F. And if I add that over here, 0.129 plus 0.966 is 1.095 F equals 333. Oh, I lied there. I kept an extra sig fig. Oh well. So that unknown force is 333 divided by that. It's about 304 newtons. That's part A. And then part B, if the coefficient of kinetic friction is 0.35, then what then is the magnitude of the acceleration? Okay, so then the normal force is not going to change, right? So the magnitude of the acceleration, well, the sum of all forces is equal to mass times acceleration. So the sum of all forces, all the vertical stuff cancels out. I have that F cosine 15 minus the force of friction. So I just have a new expression for this. So I know what F is now. It's 304. So 304 times the cosine of 15 is about, let's say, 294 minus the force of friction, which is 0.35 times the normal force, which is 68 times 9.8 minus 304 times the sine of 15. That's 206 is equal to mass times acceleration. So should be good to go here. 294 minus 206 divided by 68. It's about 1.29 meters per second squared. Now, I wish you could see all the pile of paper. You want to see the pile of papers going on here? Probably you can't fully appreciate the depth of the pile of papers. But somewhere in that pile of papers is the answers for all these. Let me see if I can find them. Oh, what's this? Oh, hey, got him. That didn't even take a long time. Okay, so this is 11, 300, and 1.3. Good. They did 2 sig figs instead of 1, or instead of 3, rather. We're good. All right, 13. A worker pushes horizontally on a 35-kilogram crate with a force of magnitude 110. A lot of boxes to push around here. The coefficient of static friction between the crate and the floor is 0.37. What's the value of the maximum static friction under these circumstances? Well, that should be easy. The max is, what is that equal sign doing there? Who put that there? The coefficient times the normal force. So that's 0.37 times the normal force in this situation, because there's no ramp, is just going to match gravity. So 0.37 times 35g, about 127 newtons, looks like. Number B, does the crate move? No, because that is enough to match this. It would, in fact, just match this. It's not going to be more than this, because if it was more than that, then it would start accelerating the other way, and that would be weird and impossible. So, no. It does not. In the French version of our textbook, the answer for that problem is no. Part C. What is the frictional force on the crate from the floor? 110. Suppose next that a second worker pulls directly upward on the crate to help out. What's the least vertical pull that will allow the worker's 110 to move the crate? All right, so let's see. If that's the case, then I have 35g, and I've got 110 newtons here, and then I would have a normal force that would now be smaller because I also have the force of that other worker pulling here, and I'd still have to snap that. I still have to get this up to 127, right, if I'm going to get it moving. So I only have 110 here. So this will have to get, I'm going to have to reduce the normal force enough so that the 110 can get it done. So let's see. What I need then is for the normal force, if 110 is going to get it moving, because I'm not increasing this, then 110 would have to be equal to the force of static friction times the normal force. So that normal force is going to have to be reduced to 110 divided by 0.37. Is 297 newtons. And what was it before? I never did actually do that separately. This is 343 newtons. So if I need to reduce the normal force down to 297 from this, well, that's exactly how hard or how much that worker is going to have to pull up. So because these two will balance this. So 297 plus this has to equal 343. So 343 minus 297 is 46 newtons. That's how hard that worker is going to have to pull up on the box. And the last part of this one is if instead the second worker pulls horizontally to help out, then how hard do they have to pull? Well, I just have to get this up to 127 then, because if they're pulling horizontally, it's not going to change the normal force. So they just have to help out to get this up to 127, so that would just take 17 newtons extra. So what's the moral of that story? If you want to help out, pulling in the direction that you're trying to pull in is going to be more helpful than pulling up on the box to try to reduce how much friction there is. So there you go. Next time you go to work, now you know. The coefficient of, this is number 15, coefficient of static friction between Teflon and scrambled eggs is about 0.04. That's pretty low, because it's a no-stick pan. What's the smallest angle from the horizontal that will cause the eggs to slide? All right, so let's see. This is the smallest angle from horizontal, going to be holding the pan at an angle. So I do have an angle here. Gravitational force. Nobody said what the mass of these eggs is, so I guess that's just mg. And this is mg cosine of I don't know what, and mg sine of I don't know what angle. And of course the normal force is going to match that. And if we're talking about that like borderline condition, then we're talking about just where the force of friction would equal that. All right, so let's see what we have. I know the force of friction would have to equal that, right at that borderline condition, and that the normal force would have to equal that. That's always true, regardless of how much we're tipping it or not. Also, I know that the force of friction is equal to mu times the normal force. So that's where my equation is going to come from. So mg sine theta, right, that's my force of friction, is equal to 0.04 times mg cosine theta. The mg's cancel out. I divide the cosine over here. Sine over cosine is tangent. So it looks like the theta we're looking for is just the tangent inverse of 0.04. That's kind of cool. So in this case, that is about 2.3 degrees. That'd be degrees Fahrenheit or Celsius. Book just did 1 sig fig. They said 2 degrees. So that's not much tip before your eggs start to slide. I don't have a pan that's that no stick. I don't know about you. I feel like I can tilt my pan 2 degrees and those eggs aren't going anywhere. I have to like turn it like 180 degrees and like shake it and get the eggs out. All right. The next one. In figure 624, we got a block on a ramp. That's supposed to be a theta there, sorry. And there's a force P here pulling it down the ramp, lined up with the ramp. Force P acts on a block that weighs 45 newtons. So that's like already multiplied by 9.8. That's the weight of it. The block is initially at rest on a plane inclined at 15 degrees to the horizontal. The positive direction of the x-axis is up the plane. And the coefficients of friction between the block are 0.5 and 0.34. In unit vector notation, what's the frictional force on the block from the plane when P is negative 5 newtons? Now this is the positive x-axis, so negative 5 is directly that way, negative 8 and negative 15. Okay, let's see if we can make a force diagram that we can sort of recycle for the different parts of this. There's my x-axis there, and of course gravity goes straight down because it doesn't care what the humans are doing. This is 45 newtons. And this is 15 degrees. So I can get numbers on those. Those aren't going to change for any of the parts. 45 cosine 15 is 43.5. And 5 sine 15 is 11.6. Right? Normal force is going to match that. And then I've got this pulling force, which has different magnitudes in the different parts, and then I have a friction force, which will have different magnitudes in the different parts. But I can figure out what is the maximum static friction. So 43.5. So the maximum amount of static friction available is about 21.8 newtons. That is how much is there. Now that is going to be resisting this and the pull. So I think the easy mistake to make would be to be looking at just this versus this, but don't forget this is on a hill, ramp, slant. So this is also contributing to the down the ramp force. So let's see. In part A, we got that pulling force is 5 newtons down the ramp. So if the pulling force is 5 newtons down the ramp, then I got 5 newtons down the ramp plus 11.6 from gravity, so the total down the ramp is 16.6. Is there enough static friction available to stop it from moving? Yes. We can have up to 21.8 newtons of static friction. So in this case, how much static friction do I need to keep it from moving? Well, it just needs to match that. It's not going to be this, because it doesn't have to be that. It doesn't need that much. It's going to be 5 here plus 11.6. And they wanted it in unit vector notation, so that's going to be up the ramp. That's in the positive I direction. Okie dokie. How about if that pulling force down the ramp is 8 newtons? Why am I not writing the -8 in the I? Because I have it in my diagram. I'm showing here what the direction of it is. So let's see. I would have 11.6 and the 8, that's 19.6. Still got enough. I can cover that. And I bet we're not going to be able to cover it this time. So how about if this is 15 newtons? If that's 15 newtons, then the down the ramp direction is going to be this 11.6 plus 15, and that's going to equal the mass of the block. They never did tell us the mass of the block, but I know that's the version that's already multiplied by 9.8, so I can find the mass by doing that, times the acceleration. Oh, and I did mess this up. The sum of all forces, those are the down the ramp ones. I left out friction. This should be here minus how much friction there is. And I know now 11.6 and 15, that's 26.6. The static friction can't cover that anymore. So the friction here that I have is going to be my kinetic friction, which is 0.34 times the normal force, which is 43.5. So what do we have here? 26.6 minus 0.34 times 43.5, and that divided by 45 over 9.8. I don't like that number. That doesn't seem right. That can't be right. What did I do wrong? Let's just try that again. 26.6 minus 0.34 times 43.5 is 11.81, and then that divided by 45 over 9.8. That looks good. Oh, I'm not sure what I did the last time, or the first time. So that's given me about 2.57 meters per second squared. All right. That's a real typical kind of friction problem. It is important to understand how to manage that. Like, is it moving or is it not? Like, is there enough static friction to keep it from moving? So I like those types of problems. Number 19, we have horizontal force. We've got a block that's being pushed against a wall. A 12 Newton force, this is. And the block weighs 5 newtons. The coefficient of static friction between the wall and the block is 0.6, and kinetic is 0.4. Assume that the block is not moving initially. Will it move? And then in unit vector notation, what's the force on the block from the wall? This is positive x-axis here, what we would think. Okay, so what is the maximum? Well, first of all, let's look at this for a second. If this is being pushed against the wall this way, the wall is going to push back. So although this is seems maybe a little bit weird, different, the normal force here, it's perpendicular. Remember, normal means perpendicular. It's perpendicular to this surface. There can't be a normal force from this wall pushing like up, for example. The wall can only push perpendicular to its surface. So that, for sure, if you've ever pushed a block against a wall, that is not going to be anything different than this. Those will balance each other. And this force of friction now is going to be up the ramp because it's going to oppose, it's either going to try to balance the forces or oppose the direction of motion. Okay, so the question is, what's the maximum amount of static friction? Got to check that first. So the maximum amount of static friction available is 7.2 newtons, and I only need 5 newtons of friction to balance that. So the answer to question, will the block move? No. No. And in unit vector notation, what is the force on the block from the wall? On the block from the wall, it's 12 newtons that way. So in unit vector notation, that'd be negative 12 I newtons. Oh, I see what the, and also this right here, that is a force on the block from the wall, that friction force. It's not like there's some other thing providing the friction, so that is also part of the force on the block from the wall. I don't know why they went throwing 2 dots next to that one. It was pretty easy. Number 21. An initially stationary box of sand is to be pulled across a floor by means of a cable in which the tension should not exceed 1100 newtons. So I get the old box cable game again. So I'm just going to max that out, and we'll just say that that force is 1100 newtons. And the coefficient of static friction between the box and the floor is 0.35. What should the angle be between the cable and the horizontal in order to pull the greatest possible amount of sand? And what is the weight of the sand and the box in that situation? Okay, so put my mg. I don't know how much mass I've got here in this box. I do know that this is going to be, we're going to max that out, 1100. I don't know this angle. Oops, dang it. It's supposed to be a dotted line. This is going to be 1100 cosine theta. This is 1100 sine theta. And this, that does not need to be dotted, is the static frictional force. We just need to break that. So we're going to set that equal to the maximum static friction, which is equal to mu times the normal force. And then the normal force, these two are going to add up to that because the box is not going up and down. So that would be mg minus 1100 sine theta. All right, so let's just write equations that show the balance in the up-down and side-to-side directions. So here I've got mu, the static coefficient, times the normal force, that's this, must be equal to 1100 cosine theta. And also, in the up-down direction, oh, you know what? In the up-down direction, I'm using that to get a substitution here. That's what I'm doing. So I'm going to make that substitution. I'm also going to sub in the 0.35 times the normal force, which is mg minus 1100 sine theta is equal to 1100 cosine theta. How's that? I think we're good. All right, now, like, what the heck are we supposed to do here? I mean, that's it. We have one equation, and it's got two variables in it. But what they're asking us is, what should the angle be to get the greatest possible amount of sand? So we're looking to maximize the amount of sand. Wait a second. This is like an applied maximum or minimum problem, which is like what we're doing in calculus right now. Are you kidding me? Okay, let's try to solve this for m. 0.35 mg is equal to, I'm going to move that to the other side, 1100 times 0.35. If you're like, oh, wait a minute, I think I know how to do this now, then you need to pause the video. Watch me do it. So let's see, I'm going to add this, which is 385 sine theta after I distribute that, plus 1100 cosine theta. And then if I wanted to solve it for mass as a function of theta, then I would just divide by 0.35 g. And I'm going to go ahead and do that to those numbers so I have a little bit cleaner look at this. So I've got 385 divided by 0.35 g. 385 divided by 0.35 g. That's 112 sine theta plus, and then I've got 1100. Actually, let's just do that. Calculator shortcuts are good. 321, call that cosine theta. Okay, so now I've got mass as a function of these things. So I can graph that, right? If I pretend this is y and these are x's, then I should be able to graph that and find the maximum. Or if you're thinking, wait a minute, I'm a calculus student. I want to take the derivative and set it equal to 0. Sure, you could do that too. Want to do it that way? Okay. So dm d theta is equal to 112 cos. Oh, we got a problem here though. If you're gonna do trig with
Students following an A hybrid schedule will attend on Monday and Tuesday, along with those attending 4 days per week. Thanks to everyone for adhering to our mask policy.
Good job, everyone.
You're doing a great job keeping everyone safe. We have a couple of bus changes for this afternoon.
Oh, bus changes.
Bus 2 will
Sorry about the interruption here. We're almost there. So we can't do the calculus because we need our answer. Well, I guess we can. We just have to recognize that we're going to get an angle in radians. Okay, so we can do it. But if you're doing calculus with trig functions, you are automatically in radian mode whether you want to be or not. So we just need to recognize that. So let's try it this way. All right. So there's that, and now we need to set that equal to 0. So 0 equals those, which means if I move, that means they have to be equal to each other. So if I made the 112 cosine theta on this side and the 321 sine theta on that side, then dividing cosine over here, that would be tangent theta is equal to 112 over 321. 0.349, so the tangent inverse. Oh, and then I could, yeah, I guess if I'm in degree mode, so I guess we can do that. Okay, that's fine. So whatever mode you're in, if the tangent inverse needs to be that, or the angle is tangent inverse of that rather, then whatever mode you're in, I guess you're okay. You do need to be careful, though, about that. So 19, the angle that gives us the maximum weight is about 19.2 degrees. What did they ask? Was that part A or B? I think that was part A. And for part B, they want to know what's the weight. So, and they're not asking for mass, they're asking for weight. So then I would have to just go back and plug that in here. So let's just store that angle as x, and then I'll do this expression, 112 times the cosine x. Oops, I was looking at the derivative there by accident. 112 sine x plus 321 cosine x, and that is the mass, and they wanted the weight, so I'm going to go ahead and multiply that by 9.8 and get about 3,330 newtons, something like that. Does that match up with the book? Yep, great, that was fun.